know there's like a lot of people. Okay, cool. Recording is working now. All right, sweet. Okay, loads after 1 minute, but processing isn't working. Okay, transforming a reflectance spectra to absorbance isn't working. Okay, well, that's good to know. So there may be some pre-processing issues going on. Thank you for letting us know about that. UK and Chrome. Hazel, I know there were some issues with Chrome that we had to overcome for like data upload. So I wonder, I'm using Chrome too. So let me try to run this. You can also, if you want to follow along. So today we're going to be focusing strictly on spectral hyperspectral image analysis. If you want to follow along using the R app, go ahead and do that. Also, if you want to go to www.openspecy.org, go ahead and do that too. It's basically going to be the same exact thing. That's the goal anyways. But if there's any questions that come up for you, let me know, or any issues with using any of those different services. But all of them should work the same way. All right. Okay, so we'll see if I end up running into any issues while doing this tutorial on this new website. I'll switch to the R interface, but hopefully this will work. So let me pull up just gonna pull up my notes here. Okay, so we're going to start by talking about what is a hyperspectral image. We're going to go over how to explore hyperspectral image data in the Open Specy web GUI. We're going to talk about how to identify particle regions in a hyperspectral image and collapse the particle spectra. We're also going to characterize the size and shape of the particles and talk about how to identify the particles using different techniques. So first, we're going to go over here and download this test map. And what that should download for you is a zip folder that basically looks like this, and it has two files in it. The first file is called an HDR file. This one has metadata. Let me see, can I look at that inside of this? Yeah, here we go. The HDR file, so this is a common file format also called an NV file. It's a combination of the two files, the DAT or sometimes the IMG file. IMG? I think it's IMG. But for our instrument, when we export NV files, it's a DAT file and an HDR file. Inside of the HDR file is where all of your metadata is. So you have it's going to tell you what the coordinate system is of the hyperspectral image. It'll tell you samples and lines. That's kind of like how many X pixels there are and how many Y pixels there are. Bands is like the number of wavelengths that there are in the hyperspectral image. If you're using your own NV file format and you want to paste in the chat any metadata questions that you have, go for it, and we can talk about them too, because every single instrument has a slightly different way that they format these hyperspectral images. So it's not like necessarily that you're going to have the same exact format for your machine. I'm really curious actually, how many people in here are doing hyperspectral image analysis right now in their work already, just to get a gauge on where people are at, because I don't want to stay too basic or get too advanced. Maybe if people can if you are, maybe paste in the chat. We are doing hyperspectral image analysis right now. Okay, cool. You use it. Okay, so we have at least a couple people. done so far. I know all the people at the Moore Institute have. I know the Gray Lab is currently working on it too. So I'll just assume for now that we're all coming in at like kind of like some knowledge, and I'll go from there. And then so you have the or no knowledge. Good idea. And so the one of the more important things in here, so you have pixel size. So a hyperspectral image is really, it's like a photograph, like a red, green, blue image. That's a multi-spectral image, right? You have 3 different bands, red, green, and blue. The pixels in a photograph have a specific like spatial dimension to them. Similarly, in a hyperspectral image, you have bands and pixels. But the pixels in a hyperspectral image are usually going to be like in a IR or Raman hyperspectral image, they'll be super small pixels. So for our machine right now, it's like 25 microns by 25 microns. A lot of other machines out there will go even smaller, down to like 5 by 5 microns per pixel. And then the bands are basically the wavelengths of light for the IR. So in our case, instead of just red, green, blue like a color image, you would have 427 bands, and each band is represented by one wavelength of light that you're looking at. Right, and then the other file is not something you can really look at. It's this DAT file, or also there's the IMG files. And this one is where all the spectral data is. So this will have the intensities in it. It's basically like a compressed, group of a bunch of numbers in there. It's just a string of a bunch of numbers, and the header file is going to tell that string of a bunch of numbers how it is supposed to be like plotted and behave when it's read into Open Specy. All right, so if that didn't make sense, it will hopefully make more sense once we actually get this uploaded into Open Specy. Is this helpful? Pre-processing works fine in Firefox. Oh, thank you. That is very helpful. We'll look into that. We'll see if the pre-processing is working for me in my Chrome, because it could also be like a Chrome version issue or something. But so I'm going to upload the test map here. And I'm just going to click around here just to see. It looks like pre-processing is working for me in my version of Chrome right now. Yeah, and that button is working. So Martine, thank you very much for that comment. I'm guessing right now that the Chrome issue is like a Chrome version thing. Not quite sure what it is, but maybe we can follow up with you after and figure out what Chrome browser version you might be using and how that might be impacting the compatibility. But good to know you already have Firefox. That's also working. So if this new site doesn't work for some reason, going over to a different browser could sometimes fix it. All right, let's turn off pre-processing for now. And so we are looking at the hyperspectral image now. So it looks literally like an image. We have different pixels here. We can hover over them. The hover data here that we're seeing is basically showing us right now, it's the signal to noise ratio of the pixels. And so if you have higher signal to noise ratio, it's going to be brighter colors here, lower signal to noise ratio, darker colors here. The signal to noise ratio for hyperspectral images, it may or may not be super helpful for kind of exploring the hyperspectral image. There's another format that we'll explore here in a little bit, but just to give you some intuition about these. So there is, I wish I had the visual image of this particle, because it makes a lot more sense. Let me Let me pull up another example with, oops, that's not what I want. Let me pull up an example real quick with a visual image companion from a manuscript that we're working on this right now. Okay. So on our machine, we can take visual images here, and we have a bunch of red beads in the visual image. And then the hyperspectral image looks like this when we turn it into a heat map. We're basically compressing the spectra to get just like a single value, because you can't really plot. You could plot a single band at a time if you wanted and make a photograph of that, a false color image. But what we're doing here in this is where we've basically calculated for every spectrum in the hyperspectral image what the signal to noise value is, and then we're trying to plot it like this so that it could be overlaid. In the image that we have in the website that we're currently working with, there's one particle. I'll tell you because I know there's one particle here in the center, and it's just a single particle, a single small particle. Now, once we have that hyperspectral heat map, we can use that to identify where particles are in the image. And you can see in this new false color image, the black regions correspond to the red particles in this visual image, which is what you want. And then we can take those particle regions, identify what the particles are. You know, are they polyolefin particles? We can get shape sizes of them. And then we can also do like a visual overlay. We're probably not going to get to this visual overlay part because I haven't quite incorporated this into the Open Specy website yet. It's just in the R package. So if you are interested in getting to this level, I think that'll be in a future training. Any questions about what a hyperspectral image is at this point? Is it kind of clear to everybody what the properties of these hyperspectral images are? Or does anybody have any questions? Yeah, Julian, if you want to type the question or if you want to unmute, go for it.
I'll unmute because it's too long to type. So I get the background. I understand hyperspectral imaging. It's remote sensing. People use that type of thing as well. But I don't have experience on the practical side. So, you know, is this we stick our filter paper under an FTIR and then stitch together some composite of images over, you know, with a 25 micron grid size?
Mm-hmm. Good question. Yeah. So so this particular hyperspectral image has a stainless steel background to it and then a particle on top of it. And so if we look at, this is going to be if we click over here, that's lagging a little bit. If we click, let's find a spot where the particle is definitely not. So this is your stainless steel background here. You can tell that this signal is just like a flat line of noise at this point. There's no more signal from your particle. There's different ways that you can present the particles to the hyperspectral imager. So the way that we're doing it right now is we're trying to collect what's called a transreflectance spectrum. Basically, we focus on a stainless steel background when we're collecting our signal, and we want the light to pass through the particles, bounce off the stainless steel, and come back to the detector. There's another way you can do it, which is a transmission measurement, and you need a different type of surface that you have the particles on for that. Really common surface people will use is an anodisc filter. It's an aluminum based filter, aluminum oxide, and that will allow you can collect the transmission measurement going straight through the filter and through the particles. And that, in some cases, is going to be higher signal. It kind of depends on what your detector setup is and how easy sample prep is for you and stuff like that. I've seen people do both. Both definitely work. So you can do either of those kind of images and then either those kind of sample preps. The main thing is you want a homogeneous, or you want your particles to be really spread out like this. You do not want your particles to be super clumped on top of each other. That's not going to work very well for the analysis of a hyperspectral image.
Okay, can I then ask a follow-up? So,
Yeah.
I mean, it's typically then this type of stitched image, if it's a stitched image, something that you would capture with a focal plane array. Or is it a faster technique? I mean, it's not just one snap that you can take over time. It's a focal plane array, and then another route for analysis might be to take that image and run it through something like Simple.
Yeah, good question. So yeah, focal plane array is one technique. Here at the Moore Institute, we have a linear array, which is similar to a focal plane array, but it has fewer. We had like 16 measurement spots that we can hit. So basically, with a focal plane array, this is a really good question. I should add this to the agenda. But with a focal plane array, you might get like a 64 by 64 grid of 25 micron measurements at one time. So you might have like this chunk here of the filter that you're collecting data on. And then you'll move up to the next spot and do it again up here in this region, and then do it again up here. And so with a focal plane array, because there's so many measurements happening at once, you go really fast. Another thing you can do, so with a linear array, the region is smaller that you're looking at, but it also goes quite fast. So we might just be like a single line here, and we'll just go up and down and kind of snake and collect the measurements, and then they all get stitched together. There's also a QCL, which I don't know a ton about the quantum cascade lasers. There's different ways that they can be configured. I know they're similar in some ways to a focal plane array, where they can kind of look at a larger region at once and collect an image. So there's a bunch of different techniques. No matter what you're using, they are definitely collecting independent spectra across your like spatial domain, and then stitching those all together spatially so that you have like an image, like that corresponds to what you would see in a visible image. Is that helpful?
Yeah, perfect. Now I've caught up mentally. Thanks.
Sweet. Yeah, for sure. Great question. Thank you. Any other questions before I move forward? All right. Sweet. Okay, so we're gonna go back over here. Okay, so this is, so when you're clicking around, you're literally looking at different locations on this particle that's here in the middle, and you can see different spectra. One thing I want to point out is that, so the particle is basically here, and we're collecting these reflectance measurements that have this stainless steel background. And so one of the side effects of this is that near the edges, you can actually get like some weird artifacts. So you'll get these spectra that are kind of like half stainless steel, half particle. You can also get regions that are further away from the particle where it almost seems like the light is kind of bouncing off of the particle and then back off. So you get there's this like halo effect around your particles with the actual information. And how bad that is really going to depend on how you prepped your samples, what your particle dimensions are, and stuff like that. But it's just something to be aware of. All right. So we're going to go into how to identify particle regions. So when we want to identify where particles are, we're really trying to get we're trying to get that image in Open Specy to look a lot like this, where you have bright regions in the particles and dark regions where the stainless steel mesh is. That's the ideal goal, because once you have that, you can then set a threshold of how intense the light needs to be defined as a particle. And then you've just defined where your particles are. There's a bunch of different approaches to analyzing these hyperspectral images. You know, some people wouldn't even add on this step of identifying where the particles are, but I find it really useful for our workflow. So like Simple, for example, doesn't do this step. Simple will just go through and run a correlation to every pixel and then use that information combined with some signal information to figure out where particles are. Pure and C uses this particle identification step. Open Specy, you can go either way. So you're flexible. You don't need to use the particle identification step. You can if you want to. I'll try to show you both ways if we have enough time. But for now, I'm just going to show you the preferred way. So we're going to start here by going over to this threshold signal noise. And we're going to change this to signal times noise. And maybe even total signal here. Yeah, total signal is actually even better. So there's different things that we can do to try to find where the particles are. This is based on the Beer-Lambert law. So basically, wherever the particles are, it should have higher intensity. And let me see, is this newer version of Open Specy? I think the min-max normalization feature is now working. Let me see. Yes. Okay, cool. All right. Let me show you why this works. Okay. So what I did is I just turned off min-max normalization in pre-processing. And what that's going to do is it's going to make the y-axis here on the spectra be the actual y-axis from the spectra instead of being min-max normalized. Sometimes it's easier to see it min-max normalized. Sometimes it's easier to see it as actual y intensity values. In this case, it's better to see it as the actual values, because what we're going to see is that when we look at where the particles are, the actual y values are higher. So your y intensity values are like, 0.2 on average or something like that, versus over here, the y intensities are in the negative values. So why is that? So basically what's happening is when you're collecting these hyperspectral images, you first collect a background. So in our case, our background is like, we're going to find a spot on the stainless steel mesh where there's no particles. We collect a background there. It's just atmospheric information, right? There's no sample. We just have a reflective surface and atmospheric information. Now, when we're over the particles, so we've subtracted that from the background. So you can get you get this weird artifact where there's like negative values sometimes. Now, when we're over a particle, there's not just atmospheric information. There still is atmospheric information, but now there's also particle information. And so now you start getting that particle information you have even more absorbance in that column where the measurement is being taken. And this is because of the Beer-Lambert law specifically, which basically states that like you're going to have higher absorbance where there's more thickness to your particles, right? So now when we take total signal, so total signal, this is the sum of all the intensity values of the spectrum. So here, the sum of all the intensity values is 700. Here, the sum of all the intensity values is 130. And you can see that when you look at this, right? Like these are all really low values. These are all really high values. All right. And so what this will let you do is basically we can figure out along this particle, especially looking at its edges, we can identify a threshold for the total signal that will basically make sure that we're just getting the particle spectra. So we can look at this spectra kind of at, you want to keep it like at 1,000-foot view when you're first trying to set up this particle ID routine. But basically here, it's like, yeah, that's not really the particle anymore. So somewhere around like 200, I'm not getting good signal. I don't like that. Over here, let's see. Yeah, definitely starting to degrade the signal around like 200. But then this is like really clear particle signal around like 400. So maybe like 300 would be a good threshold to use here. So we can go back here and we can set our threshold, our minimum value to 300, and then turn on threshold signal noise. And what that'll do is it'll crop out the background from the image that we're looking at. So now all the background is black, and your foreground is just where your particle spectra are. And so we can inspect that and just kind of make sure that we like how that's been cropped. And with one particle, it's a lot easier to do this than with a lot more particles. Oh, is there a question?
I made the second half, you know.
Oh. So I'm going to mute Gwen. What does good signal mean? That's a very good question. So good signal is one of those things that that's a little bit of an art to define. So one of the things that you could use to define good signal is your signal to noise ratio. That's a very classic approach for defining good signal, which is basically the highest peak divided by a low region. And so what you want to have is you want to have like a really big peak and a really low flat region in your spectrum. In reality, it's more complicated than that because, for example, in these spectra, we have these high peaks that are due to CO2 influence. And the CO2 influence creates this high peak, but it's actually an artifact that we're not interested in. And so you can have high signal to noise ratio on this spectrum because of an artifact. So that's one thing to think about. Another thing to think about is how noisy the spectra is. And when we're thinking about the noisiness of the spectra, we're looking for like very tight undulations, tiny like sharp peaks, and how high those are relative to the real peaks. So here, like this region, I know this because of these spectra, but also like peaks are not usually this sharp and this tight together. So this is noise here. This is probably a peak. This is probably a peak. That noise region is pretty similar in like its height off of the what we call the baseline. It's similar in height to the peaks. And then there's the last piece of it is baseline influence, which we're not really thinking about too much. Actually, the baseline, we're using it here to find where the particles are, because the baseline is going to shift too. With wherever the particles are, the baseline is going to go way up. So it's a helpful thing in this case. Is that somewhat clear? I know it's a little bit of a fuzzy answer, but unfortunately, there's not like oh, this is good signal, this is always bad signal case. It somewhat depends on your use case. for microplastics research or like particle research, when we're doing this kind of analysis, I think those are the main things to be thinking about, is like signal noise ratio, artifacts, and then how noisy the spectra is. Is there a percent value that we should be concerned about a bad good signal? Oh, interesting. Percent value that we should be concerned about. I'm not totally sure about what the question is, Julian. If you want to unmute and ask
Yeah,
it.
yeah, I'll unmute. I mean, just above your image there of your particle, it says good signal 63%. It says that on mine.
Right.
And so is that, it seems to be a metric. Is there a point where I would say, oh, it's only 20%?
Right. Yeah. Oh, sorry. Thank you. I forgot about this bar up here. Yeah, so good signal 63%. That's basically just saying 63% of the pixels are above our threshold that we set up here, this threshold signal noise. It doesn't really matter what this is for hyperspectral images, because if 90% of your spectra or of your pixels are background, then this would say 10% good signal. Yeah, so hopefully that's helpful. All right, we may not get all the way through everything today, so we'll definitely have another training on hyperspectral image analysis that'll go into more depth on some of these topics too. All right, so once we have this thresholded image that we like, that looks like, okay, I see what I was expecting from my visual image. This looks like the particle that I thought would be in this hyperspectral image. There's a couple of things that you could do at this point. One thing is you could just go ahead and start doing identification on it and see what you find. So maybe we start with that because it's pretty straightforward, and then we can talk about the different techniques of collapsing particles. So, all right, so we'll do a pre-processing on the spectra. I'm gonna add in min-max normalization here. And then we're gonna do identification. And in this, if you're with me and you're using the new version of Open Specy, it's using a smaller library than the previous library that we've worked with in the past. And it's a medoid transformed library, which is basically, we've identified spectra that are redundant and removed those from the library while trying to maintain a high level of accuracy. So it still should be very accurate. And now the hyperspectral image has transformed into an image that is, when we hover over it, it's telling us the identity of the pixels. So you can see here it's saying cellulose derivatives is what it's identifying that particle region as. It also has some identities over here like polystyrenes, polyhaloolefins, other materials. So it has some pixels that it is identifying as something. And as something else. But I know for a fact that there's one particle in here, and it's a cellulose derivative particle. Similarly, we have another threshold here, which is threshold correlation. So I'm going to remove the threshold signal noise. That way we can just see the impact of the threshold correlation. This is also very useful because you could say, well, my background shouldn't be highly correlated to the library spectra because it's all noise. And so you could have also just said, all right, yeah, let's let's use identification. Let's identify what all the spectra are. And then we see this particle pop out of the background, this one cellulose acetate particle, cellulose derivative, and that's your identity. You're like, okay, great. I have one cellulose acetate particle. Awesome. Again, just for everybody's memory, we can look at the top matches of every spectrum. So if you want to see, like, this one, let's say that you didn't like this match very much, you could look at the top matches by pulling this up here, and you could click through them and see the other identities of the like the top 5. I think it goes up to like 2,000 spectra or something in this smaller version of the library. And you can click through them and just compare those visually to the match that you have here. All right, so that's kind of like, that's the manual approach to analyzing this data. At this point, some things that you want to get out of this a lot of times is you want to get the polymer type, you want to get the particle shape and size. Those are some different things you want. So size would be easy to get manually. We know that every pixel is 25 microns here. We can take a look at this. The y-axis goes from like 1 up to 12. The x-axis goes from 0 over to 15. So you have 16 pixels on the x-axis and what is that? 11 pixels on the y-axis. Multiply each of those by 25, and now you have your particle dimensions. You could use that to calculate aspect ratio, which is a shape parameter. You could use the estimated area to calculate circularity and some other things like that too. So if you want to do like quantitative shape analysis, that's basically what we're doing. I'll show you. Open Specy already can do this automatically too. And there's a couple of different ways that it can do this. So since we're already here, what I'll do is I will show you how to export the data for thresholded particles. Interesting. I think this will work. Let's take a look at this. So I'm going to open up this thresholded particles here. And it's saying that there's one particle that's been thresholded out of here. It has the area dimensions in it. So it has your area this is in number of pixels. It has the perimeter of the particle. It has the ferrite min, ferrite max, convex hull area, which is like kind of the area of the connecting points around it. Ferrite min and ferrite max are like your min max dimensions in number of pixels. And it also has centroid, X, and Y location, so like where the particle is in your hyperspectral image. All right, and so why did it only identify one particle here? Why did it only give us one row? Basically what happened is it's going to use whatever thresholds you specify. It is going to use the threshold correlation because that's the only one that we specified right now. We don't have threshold signal noise turned on right now. So it thresholded by correlation. It figured out that there's a continuous, highly correlated region here. And it's just using the correlation values right now. It's just like all of these pixels, every pixel that has high correlation, I'm going to lump those all in and say that's one particle. So basically, it is adding in these other spectra here that may not be super high confidence, but there's still higher confidence than some of the other ones. And then what we can do, hopefully this doesn't crash anything, but this is a good test. We can upload that thresholded particles spectrum back in here and identify the thresholded particle spectrum. That doesn't seem right. There's something lagging here. Hazel, definitely write this one down. So when I uploaded a single spectrum, the map information should have disappeared, but it's still using the map information. So we need to do some like refreshing or something. Let me just refresh here, and then I'll upload that that thresholded particle, because basically what, and that was a lag that it had. So this is one good way that you could get representative spectra for your, if you just took hyperspectral images of single particles and you wanted to use all the spectra over that single particle to try to identify the particles, this is one way that you could do that. So now I'm going to re-upload the thresholded particles spectrum. Okay, that looks better. I actually need to turn off pre-processing because when we did the thresholded particle export, it was already pre-processed. So now our thresholded particle spectra is already processed. And this is what it looks like. That's classical cellulose acetate spectrum. And we'll get a very high match here, 0.99 to cellulose acetate. And then you can look at the top matches here. And last, you could export the top matches, download that, and then pull that up. And then in that, in this export now, we still have particle shape and size information for that particle, right? But now we also have identification information. So it's going to tell us, it's going to add on what the material class is. Let me make this bigger. It's going to add on what the material class is that it predicted. It's going to add on, let me see, signal noise values. It'll have a ton of metadata. There's so much metadata in this library. It's also going to have correlation strength, match values, correlation strength values here. All right. Let me pause there again if anybody has any questions at this point, because what we just did our first hyperspectral image analysis on a single particle hyperspectral image. You basically were able to get particle dimensions and particle identities pretty much automatically with that. That would also, that same approach that I just showed you, if you had 100 particles, 1,000 particles on your image, it would also work. But just for it's going to be a lot slower when you run a larger image. So just for brevity for this tutorial, where I'm just showing you the single particle. Okay, not hearing any questions. That's good. So let me show you in this last 10 minutes, I'll show you the other way that I more commonly do this analysis. Oh, okay. How do you download the updated file? Okay, so I think that you're wondering about the final file that has all of your data in it. So yeah, you'll go to top matches, and that'll give you top matches is going to give you the identifications of every single spectrum. And then thresholded particles is going to give you basically a whatever thresholds you have defined here when you were doing the hyperspectral image analysis, that it will compress the particles. And what it's doing is it's taking all of the spectra for each particle and it's taking the average of them so that you only have one spectrum that you're analyzing. So now we went from like, I think there were about 100 spectra for that particle region that we defined. And now we're just analyzing one representative spectrum. There's different ways you can do this kind of analysis though, of course. So hopefully this is like general enough. And I'll show you one other way before we jump off of how to do the hyperspectral image analysis. Hopefully when I upload this map, that will work. Let me see here. Yeah, there's definitely some lagging issues going on. Now that Hazel, another thing I just noticed, when I unselect identification, it doesn't remove the identification plot. I think we just need to specify the reactivity differently in this so that it's a little bit more consistent. But okay, so I'm going to try to upload the test map again. Okay, cool, that worked. And we have our test map spectrum again. So another thing we could have done is we could have just, instead of doing identification, one thing about identification is it's really computationally expensive. It's one of the most computationally expensive steps of this entire analysis. And so if you go straight to identification, it could be really slow. Like it could take hours or days even to analyze your map versus the thresholding by signal noise is super fast. So this, if we go threshold signal noise and we go back to total signal, this process is very cheap, very computationally cheap. So if you can find where the particles are just using the spectral information without doing identification, you've saved yourself a lot of computation. Also, sometimes it's more accurate. So for example, with this, what was it? I think we wanted it to be, I think it was like 300 that we had decided on. 300. So this region here is actually a little bit, I can just tell you based off of my experience here. I wish I had the visual image for you too, but this particle that we're looking at here, this is more a better accurate representation of where the particle is than the correlation heat map was. So if this is also more accurate, then that's also a bonus of doing it this way. Where this tends not to be more accurate is when you have touching particles, because the correlation can actually, if you use the identifications in the correlation, you can also split the particles up based off of what they're identified as. So there's trade-offs to everything. But what we'll do here is, so now that we've defined this particle region, we're going to do the same exact thing as we did with the correlation. We're going to download the thresholded particles. Oh, what? That's not working. Interesting. Let me see. Is it because pre-processing is not turned on? Is that what's going on? Let me try this. Okay, that worked. Another bug, Hazel. It's a squash. I guess the thresholded particles won't download unless pre-processing is turned on. But we want it to be able to download as long as threshold signal noise is turned on. Sometimes you don't want to have pre-processing turned on. But I just turned off all of the other pre-processing things in here, and that works the same as like turning the pre-processing off. Okay, so now we can open up that file, take a look at that one. We could even compare these across, like what's the difference in the area that we found. So this area is 131 pixels. The other area was, I forget what it was. $180. So definitely a difference here in the the region that was specified for using just the signal values versus the correlation values. But then we can do the same exact process as before, where we uploaded the thresholded particles, and that's our thresholded particle spectrum. This one, because we haven't done any pre-processing on it, this one is actually still the raw spectra being averaged. And so this one, we will want to turn back on the derivative, the conforming wave numbers, because those are going to be important for the identification step. And you always, the number one things to always turn on before you do identification are going to be the smoothing derivative and conforming wave numbers. Min-max normalization is like optional, but yeah, generally it's a better idea to min-max normalize. Okay, and then I just did identification, but this is also weird. So for some reason, the plot isn't responding right now to the update, but basically what it should be showing us here is the overlaid spectrum in red on here. So if you start getting some issues like this, I'm not sure if this issue would be present in the openspecy.org. It probably wouldn't be. These are just some new issues that we're trying to resolve in the beta version of this WebAssembly version of the app. So it is still, for some reason, it is still showing us actually the metadata of the top match, which is nice. And you could still probably download the top matches, and it would give you, the same information as before, because it's also coming up as a cellulose derivative with a high certainty. Okay, we just have 2 minutes left. I'm gonna stop again if anybody has any questions. I'll also stay on for a while too if anybody wants to talk about anything specific. Thanks a lot for joining. I think the next call will be we'll be diving into this a little bit more in detail, probably using the R console to actually analyze some very large hyperspectral images, which once you get into like 100,000 spectra, it stops making sense to do it in this way. It's not as easy to do it in this way as it is through the R console. So we'll be using some code there. All right, stop presenting. Cool. Thanks everybody for joining, and hope you have a good rest of your day. Let's see. When's the next call? Asking because this session shows on my calendar for last week on the 9th. Interesting. Yeah, not sure why it didn't update for you. The next session is going to be, let me look on my calendar. Find out when that is. October 23rd is when I have the next session for. Are you seeing that on your calendar, Martine? October 9th. Huh. Yeah, strange. Oh, okay, it's something you put on your calendar. I see. Let me, do you have you want to put your email in the chat and I can try to get you added to this calendar invite. So that way when I'm updating it, it should change for you. Okay, sweet. Huh, it has you already updated or already added to this calendar invite. So I'm confused why it's not updating for you on your calendar. Sorry about that. I'm not quite sure what the issue is, but oh, okay. So it's some updating issue. Yeah, weird. Yeah, sorry about that. I don't know for sure what that issue is, but I'll look into it, try to figure out what's going on. Hopefully, there's not that same issue for other people. But thanks a lot for jumping on. All right, sweet. Ingrid, any questions?